All right, today's demo is the one that ties it all together. And let me show you how. So you have the SCUTTLE Robot here in yellow. Okay. And he's getting controlled today by the Gamepad, the Xbox style Gamepad. All right, and the connection here is with Bluetooth. Let's get a little bigger. Okay, and then SCUTTLE is making connection over to the cloud via Mqtt. Mqtt is the protocol by which messages are going to get sent with a topic and a payload. Those two pieces of information are the critical parts of the message. And this is happening with an action called publishing. Okay, and this is not publishing, only the pink one. All right, and then secondly, we've also showed you on another occasion how you can have the ESP device, which is an Arduino programmed gadget. In this case, it's I have this cool one that supports an 18650 battery, so it means it's a standalone device that's what they call it, a Wemo something. That's if it's branded. And this is a super affordable $9 on Amazon gadget, and it's communicating over Wi-Fi. So you have this action going on here. Today it's listening, so we're not publishing, instead we are subscribing, and this arrow is going this way, not that one. Okay, to the cloud using the same topic. That's how you receive the payload. Okay, and I've already shown, in addition to that, also how your PC this can also perform the publishing and subscribing, and we've tested it in other videos, and briefly today we're going to do this publishing to make sure, verify the communication is received by the other devices. Okay, but we also sub, and the reason is that we are just doing some debugging. This is just so convenient to do in the web browser. So we do the sub and we listen on the same topic that we publish, and then that all works. Okay, and then today's hardware, before I get to that, let's finish this off. We also have the mobile phone demos, and there's a couple of them so far, but there will be lots more because mobile phones are useful. Using simple apps, okay, for Mqtt, such as Mqtt tool. That's just one of many. And we do the same thing. We publish to send commands, and we subscribe. And then, well, how do we know that this little device here, the ESP device, is getting the right information? Well, that's what today's all about. A cheap little simple 2-wire speaker. So let's stick with yellow. And what does it do? It's not even a speaker, it's a buzzer. So this is transmitting whatever is showing up here is also going here, and then we get a buzzing sound today. And then that means without any interface such as the serial port, without any wires, without any displays, you know that this little guy is talking and listening, and it's all standalone because it's on this battery, this 18650. So I think that's fantastic, and the price is unbeatable. This is 5 years ago, this would have been unheard of, and it was unheard of. And what's the last parts of this? Oh, the last part is how. Wow, that color is intense. Let's dial it back. Oh my goodness. Okay, so how are we doing this publishing and subscribing here? When what's the organization for this? Okay, this is through a web GUI for free by HiveMQ. Okay, and then on the Scuttle side, we say how. And that's in reference to this thing here. How are we publishing through Scuttle? On a wonderful thing called Nodered, which is a tool. Of course, we could install a library in Python and just go straight from a Python script to communicating and publishing. But Nodered is awesome because it can stand alone. When you're not running any other software on your Linux machine, you can just have the Nodered start up in the background and go automatically listening or communicating on these channels about stuff like your battery. Okay, runs in the background. And then what else have you got? When you install the Nodered. Oh, this is the beautiful part. It is so versatile that it can be installed on Windows through Python. It can be installed on Linux. And it also, there's other options. But it's a fairly universal tool, and it's fairly lightweight because I've run it on both the Pi and the Beagle and other machines very smoothly, and I'm just so impressed because it looks nice. You don't have to take my word for it. This is, I mean, it's in several of our demos. Okay, and then the last part is what's going on here. What's my computer? That is. It can be a Beaglebone Blue, which we have used, tried, and tested a lot. It can be a Raspberry Pi, or it can be a Jetson Nano. Honestly, it can be any embedded computer, but this is one that sounds really exciting to start up soon because people are writing pretty advanced scripts that will work on Nodered and do really nice stuff like interpreting information from photos and doing algorithms that text-to-speech type of stuff and speech-to-text and writing files and saving them in the background. So here we are. Oops, that's my other revisions up here. Okay, so here we are today connecting so many of these pieces and just watch and learn. Okay, so this here is a super simple diagram showing the buzzer is connected. There's a button connected too, but we're not using that for this video. And up in the corner, you can see the actual device on my very crummy webcam. Okay, there's a button on the left. 4 pins are connected and the little buzzer. Okay, so we grab the web browser and I'll show you where it is. So we just have this thing here. It's a HiveMQ, and my topic is this, and the message is, let's just test out one. We're requesting a certain sound between 1 and 9, which is in a library I'll show you next. Okay, so let me just hold the buzzer next to the microphone here, and I'm going to do 2, publish. Need to make sure that I'm subscribed here. So used to be Buzz code, now we're on Buzz. We're going to subscribe to our own. 3 and go. And we can see that we received it, and you can hear audibly that the little Wemos device also received it. This thing just does not want to show itself, and it's terrible. Okay. Next, let's check out the Nodered code that's being installed on this is on the Raspberry Pi or Beagle if you're using a Beagle. Okay, so you navigate to Nodered, and then you can see everything up here is from my previous video, so that's all explained another time. All you had to add now is a watch node that's checking this file, tmp/buzz code, with a camel case with a capital C for the second word. Okay, and our text file has a camel case. Then read the flag. So when this first part changes, if there's a detected change in that text file, then we're going to read the very same file. Okay, and then we're going to send out a message on the HiveMQ broker, which is already configured, on this topic, and the payload is going to be simply whatever's inside of this file. The output is this string. So next we show you where in the code are we producing this information that's in the text file. Okay, so this is another recycled piece of code that I will just highlight the important part, and the rest is in existing demonstration from previous video. I have 2 videos talking about CSV files, extracting values, and sending out Mqtt. So this is the main piece. We can delete that stuff. Control+. Let's get this bigger. Let's pop this tab out of the way. Okay. So, and you can see it's running because it's printing out the 5 dot targets. Okay, so this block of code is of interest today. We say if the axis 1, which is the forward joystick movement on the gamepad, is not 0, that means maybe it changed to 1. We say if our existing flag isn't already high, that means this is being changed right now. If it's, okay, so then that statement's true. We're going to raise the flag high, and we're going to send out a message with the value 1 on this function called BuzzMessage. Okay, the elif is not necessary. I'm a novice at Python, so I tried some things that didn't work. Next, if the axis 1 is 0, and we're checking if it has changed to 0. We checked that it wasn't already 0. We toggled the flag to 0, and then we generate this stop request. And the only difference between a start and stop request is what kind of music we're going to play. Okay, and then let me show you BuzzMessage. It's here. We're importing our log level 2 file, so L2 log, which is part of the SCUTTLE architecture. And we're going to log a temporary file using the argument message code and into the file named buzzcode.txt with the camel case. So this is the file Nodered is reading. All right. The only other piece that you need to know to repeat my work is to have this A1 flag declared. I declared it before the loop so that it's not getting declared and taking up processing to re-declare it every time. And it started out as false. When you call it false, then it's stored in Python as a Boolean kind of variable. Next up, we have Arduino. So how did we program the Wemos device or ESP device to do the handling of the, oh my goodness, no, simple receive. This was an example I started from. Don't have time to explain how I produced the code. I'm just going to show you as an intro. So Mqtt Buzz. The important part is that you can't see my Wi-Fi password. And here we are, section for interval, not so important. Okay, this is the section. This is the part of the loop that runs constantly. And all it does is it's pulling the MQTT. It's pulling any channels that we're subscribed to. I won't have time to explain this code in this, but then it assigns the integer payload, which is what was the payload in the MQTT message that I'm subscribed to, which is I'm only subscribed to one channel. It assigns that to something called my sound, which was declared as an integer also. And then it says if my sound has something in it, which is non-zero, then I'm going to do this routine where I print it out on the serial, which you're not going to get because we're only connected over Wi-Fi. We're not doing any talking to the computer directly. We perform a buzz chirp using that value, and then we reassign the value to 0. And if we go to buzz tab, it's all based on the cute buzzer sounds.h. and you could be doing a fart, but instead we're doing, what did I say? On this case, when we start driving, we're going to send a 1. When we finish driving, we'll send a 6. Based on my research, these are the most appropriate sounds for starting and stopping driving. So 1 is going to be this, and 6 is going to be 2, 3, 4, 5, this, happy. It's happy when it finishes driving. So this is also a poorly made kind of C programming. You can do this better with a case statement. I understand that. But this is all proof of concept. So ASCII is the form of lookup table where when I send an integer 1, it's read in as a character, and then I have to reassign that to be an integer. Okay, it's becoming a 49. Google ASCII characters if you don't understand how that works, okay? And so there it is. We upload it. We do tools, board, and probably several options will work, but right now I'm dealing with the Lowland Wemos D1R2. Oh my goodness, a mouthful. Okay, and the only difference I've found that makes right now, aside from generic SB, is we import it, and what do we do? The difference that it makes is the pin assignment. Buzz tab. Okay, D4 has a meaning, and D3 has a meaning when you're using that that board selection. All it means is instead of just giving an integer that corresponds to the actual microcontroller's pin, which is quite confusing. I can show you right now. Right here, if you look up the data sheet on this device, which you don't want to have to do unless you need to, then you're going to find out that the pin numberings do not match this silk screen. Anyway, that's all trouble for me, not trouble for you. You just copy. And then let's try it out. Okay, so I'm running the Gamepad Demo. In this mode, I drive forward and backwards. Okay, and I can turn. This is just an exact copy of a previous demo. There's no control on board or here except for interpreting these two axes. And then here we are, activated the Wemos device. And what it's going to do is when I start driving forward, or actually when I start doing any X direction movement, which is forward or backwards, then this is going to detect a change on the Raspberry Pi in the Python program, and it's going to send the MQTT message, and then when I stop driving, it'll detect the flag has changed again, and it'll send a different message. So here we go. It's hard to hear the startup one because the sound of the motors, but here we go. Let's do one more time. It's just lightning fast. So here you have a system that responds so fast that you could almost treat it as part of the robot. And you could mount this on the robot and you could have it controlling a speaker or lights or anything that you want to offload processing power, especially for microcontroller level speeds instead of microcomputer level speeds, right? And if you have a team with multiple people, then you can have some team members working on part of your technology completely independent of the other part of your technology. You can have your software written separately. You can have testing done separately, which is really important because this stuff is honestly getting pretty complicated. But now you have a way to expand. Look at how fast this is. That data is going to Singapore and back, in my case. But in your case, it's probably going at least several hundred miles to the nearest cloud server for all the passages along MQTT and back instantaneously. And, well, not instantaneously. You can see it. There's no editing tricks here. So now you have everything but 100% reliability, right? Because independently, this can lose connection to the Wi-Fi. This can lose connection to the Wi-Fi. But there are many tasks that that loss of connection can be acceptable temporarily. You can detect it. You can have your robot programmed to complain about it. And we're just opening so many doors here. And in my next test, I really want to find out how long can I make this battery last? Can I make it sleep? And can I have Scuttle distributing devices that are like sensors or other modules around a facility and then come back and collect them and have the devices telling Scuttle when they need to be collected because their battery is low, or when there's a condition where Scuttle needs to come take an action. So there you go. Hope you learned something. Here's a quick demo, MQTT from the cell phone to the ESP device. Okay, we're choosing message 8. Hit publish. Boom, it received it. Let's change to a different sound. Let's try number 5. Okay, publish. 7, publish. There you go.